The security of modern embedded systems hinges on the correct implementation of cryptography. However, analyzing these implementations presents a significant bottleneck for security auditing. Traditional reverse engineering is manual, non-scalable, and fails to generalize across diverse instruction sets. To solve this, we, Team Maverick, came up with an innovative solution, Sherlock.
Sherlock is a framework developed to detect and classify cryptographic primitives such as RSA, AES, MD5, and SIH256 within multi-architectural black box firmware binaries including x86 and ARM. Our approach is data-driven and grounded in academic research, employing two distinct methods to achieve this: a classical machine learning approach and a state-of-the-art deep learning methodology. Now, let my friends break down the entire approach into phases and walk through them one by one.
So starting with phase 1, data synthesis. To train a robust model, we must overcome the lack of pre-existing labeled datasets. Our strategy is to synthesize one. First, we use OpenSSL to create small C programs that implement specific cryptographic primitives such as AES, RSA, SHA-256 algorithms. These files we represent are positive class. Then, we use equally complex but non-cryptographic libraries such as zlib and cjson parser to create our negative class. Finally, we compile the programs we created for multiple architectures, primarily x86 and ARM using cross-compilers. Also, each source file is compiled with multiple optimization levels as they significantly alter the machine code. This process yields a high-quality datasets of hundreds of labeled binaries. Next, we move on to phase 2.
Phase 2 would be feature extraction. Once we have our dataset, we process each binary. A file's ELF header is first passed to identify its architecture. Then, using a reverse engineering tool like Hydra, we iterate through each function and apply feature extraction methods for the two approaches, classical and deep learning. Moving on to the classical approach, this method relies on carefully engineered features that have been proven effective in prior research. These are the two broad types of features that we are going to extract. First one being statistical features or opcode engrams. Using a disassembling engine, we convert each function's machine code into a sequence of assembly instructions. We then calculate the frequency of n-grams, which are sequences of 2 or 3 instructions. This is more robust than simple instruction counts because sequences like add, XOR, all carry significantly more context than a single instruction. Secondly, moving on to the structural features or CFG metrics, on the control flow graphs or CFG of each function, we calculate a vector of numerical properties that describe its shape and complexity. These include the number of nodes or basic blocks and edges, cyclomatic complexity, a measure of branching, graph density, and these are the two feature sets which are going to be concatenated into a single vector for each function. Moving on to the deep learning approach. This approach uses a neural network to learn features automatically, capturing more deeper patterns. These are the two broad kind of features that we are going to extract. First one being semantic features. The sequence of assembly instructions is fed into a pre-trained transformer model like CodeBird. The model treats the code like a language and outputs a single dense vector or an embedding that represents the semantic meaning of the function. Next broad feature is structural features. The CFG or the control flow graph is fed into the graph neural network. The GNN learns the topological patterns of the graph, the intricate loops and branches, which are the characteristics for different algorithms, and then it outputs a structural embedding.
Moving on to phase 3, model training and classification. The classically engineered feature vector from phase 2 will now be used to train an ensemble classifier like random forest or XGBoost to perform multi-class classification for various cryptographic primitives. The semantic and structural embedding from the transformer and GNN are concatenated into a single input vector, which we shall use to train a multi-layer perceptron with a softmax or sigmoid output layer for classification.
We have shown you how our project Sherlock addresses manually auditing black box firmware, one of the biggest bottleneck in embedded system security. Our data-driven multi-architecture framework, backed by both classical ML and state-of-the-art deep learning methodologies, can automatically detect and classify cryptographic primitives across diverse binaries. This is a massive leap forward from non-scalable traditional reverse engineering by successfully completing our 3 phases from a novelly synthesized dataset to robust feature extraction, and finally to training our powerful ensemble and deep learning classifiers. Team Maverick has built a tool that ensures the security of model embedded systems hinges on correct cryptographic implementation, not on manual efforts. Our next step is to integrate Sherlock into a seamless production-ready security analysis pipeline, making this critical capability available to the industry. Thanking you, Team Maverick.